These are the solutions to homework number 29, otherwise known as the practice quiz for quiz number 6. So questions 1 through 3 refer to the graph of f of x given here. And number 1 says estimate the value of f prime of negative 2 graphically. So at our function's negative 2 location, which is right here, we want to estimate the value of f prime. And so for us, that means that we want to estimate the slope of the function at that location. And to do so graphically, we're going to sketch a tangent line. So we'll sketch a line, make this a straight line. I'm going to continue it down here. And with this line, I'm going to estimate the slope. So I'm going to use 2 points on that line that I sketched. Those 2 points will be, in this case, negative 3, negative 8. And this location is 0, negative 1. And I'm going to estimate the slope at that location. So f prime of negative 2, which is equal to the slope at x equals negative 2, is going to be calculated as change in y over change in x. In this case, my y2 will be negative 1 minus my initial y of negative 8, all over my final x value of 0 minus my initial value of negative 3. And so if I put this in my calculator, we find a value of approximately 2.3. And so that is going to be my estimated value of f prime of negative 2. Now, number 2 says, with the value we found in number 1, let's write an equation for the line tangent at this location. So we have 2 things that we need to do in order to write the equation for a line. We have the slope, and we need a point. So the slope, we've already decided from number 1, is positive 2.3. And the point that we're going to use is this location right here. So our point is just going to be negative 2, comma, negative 6. And so using point slope formula, our equation would be y minus negative 6 equals our slope, 2.3, times x minus negative 2. So let's clean this up a tiny bit before we say we're done. And we have y plus 6 equals 2.3 times x plus 2. And you are welcome to leave it in this point slope form. If you wanted to change it to slope intercept, that would also be fine. Now, number 3 asks us which is greater, the slope or the derivative at x equals negative 1 or the value at x equals negative 1. So looking at our graph, we have a couple things going on. I'm going to change colors for this question. So at x equals negative 1, the value, so f of negative 1, is equal to negative 2. And our slope is going to be positive, right? Slope is very obviously greater than 0 at this location, right? If we sketch a tangent line, it's increasing. So which one is going to be greater? Well, the answer would have to be f prime of negative 1. F prime of negative 1 is greater than f of negative 1 because, and there's a few things, the slope is positive at that location, and the value of f of negative 1 is negative. And since positives are greater than negatives, therefore the slope or the derivative at negative 1 is greater than the value at negative 1. Question number 4, we have a multiple choice question. And it says, which of the following statements is true? Justify your answer. So we have a lot of different comparisons between 0, the value of our function at x equals 1, and the value of the derivative of our function at x equals 1. So at x equals 1, this is our location on our graph. And so the value of f of negative 1 is negative. It is less than 0. Then if we go and look at our slope, so if we sketch a tangent line here, or just think about the slope, which is equivalent to our derivative, we see that that is greater than 0. Therefore, what we can say is f of 1 is less than 0, and 0 is less than f prime of 1. So which answer corresponds to this? Well, it would have to be E. And for this exact reason given right here. For question number 5, we're given a graph of the function below, and we know that this red line here represents our function f of x, and we want to find the coordinates of the points A, B, and C. So this is just an application of what we did in the first 3 questions. So the first thing is we'll do B because it lies on the function f of x. So B is going to have an x coordinate of 2, which is very obvious, and the y coordinate is the same as f of x. So at 2, our function has a value of -3, so B is therefore going to have the coordinates 2, -3. Now, to find the other 2 points, we need to utilize the fact that the slope at this location, and therefore the slope of this line, is equal to f prime at 2, which is given to be 2.5. So let's get an equation for this blue line. That would be y minus our point B, y value, which is -3, equals our slope, 2.5, times x minus our x value at B, which is 2. So, cleaning this up a little bit, we have y plus 3 equals 2.5x minus 5, and then y equals 2.5x minus 8. So this is the equation for our line. So A will just have an x coordinate of 1.8, and then our y coordinate will come from this equation. So we will say y equals 2.5 times 1.8 minus 8. Plug this in your calculator and you get -3.5. So our A has a y coordinate of -3.5. And that's our A coordinates. For B, I'm sorry, we already did B. So for C, our C will have, let's write it over here. Our C will have an x coordinate of 2.1. And then our y coordinate will again come from this equation. So we have y equals 2.5 times, now 2.1 for our x, minus 8. So again, plug this in your calculator, and you get a y value of -2.75. So our C coordinate in the y is 2.75, and that's negative. So there are our 3 coordinates for A, B, and C. So for questions 6 through 15, we're referring to A, B, C, D, E, F, and G, which are points on the graph of f of x. So just to be clear, the red is y equals f of x. Now, where is the value of f of x the largest? Well, this is just the highest point, and therefore, this would be at location C. Now 7 says, where is f prime of x the largest? So we want to know, when is the slope the greatest? So let's sketch some tangent lines at each of these locations. So A will have a tangent line and therefore a derivative that is very positive. Let's use a slightly different color here. So let me make it a little thicker. So we have a tangent line approximately like this. We have a tangent line that is approximately like this, this, and so now we have all of our tangent lines. Let me do a little better with the G. So when we go through and we want to know when the slope is the greatest, the most positive slope is going to be right here at A. This is when our line is the steepest. So that'll be when f prime of x is the largest. Now 8 is asking for when are the values of the function greater than 0? When are they positive? So there are multiple locations where this value is positive. So B is positive, C is positive, and F is positive. E is, of course, not, because 0 is neither positive nor negative. So for 8, our answer should be B, C, and F. Number 9, now be careful, asks when is the derivative greater than 0? So at what points is the slope positive? So at A, we know that the slope is positive. Also at B, the slope is positive. C, the slope is 0, so that's not right. D is negative. E is positive. F is 0, and G is negative. So these are the 3 points for which our derivative is positive. 10 asks, when is the value for f of x the lowest? So A is almost the lowest, but it turns out that G is slightly lower than that. So our lowest point is at G. 11 asks for when is f prime of x the lowest. So this is the most negative. So the slope, we'll say, is most negative. So out of these points, the tangent line with the most negative slope is at G as well. So that is our location when f prime of x is the lowest. For number 12, we want to know when are the function values less than 0. So the function values that are less than 0 are at A, D, and G. These are all negative values. Now 13 asks, when is the slope or the derivative less than 0? So we have negative slopes at D and G, we have negative slopes. So when is the value for the function 0? So the only location out of these where the value of the function is 0 is at E. That is where the function crosses the x-axis. And 15 asks, when is the value of the derivative 0? So when is the slope 0? So we have two locations based on our tangent lines. C has a 0 derivative and slope, and F has a 0 derivative / slope. So we have C and F. For numbers 16 and 17, we have a toy rocket that is rising vertically in such a way that h of t, the height, is given as this function here. So how high is the rocket after 4, 5, and 6 seconds? So what we can do is we can take h of t is equal to negative 16t squared plus 200t. And the best, most efficient way to do this is to plug this into y1 in your calculator. So I'm going to go ahead and do that real quick. And once I plug that into my calculator, I'm going to go to my table, which is hopefully still in ask mode. And this is still on our calculator. And we're going to find the values of h at 4, 5, and 6 seconds. So all we have to do is type in those x coordinates and read off of our values for y1. So for 4 seconds, my table gives me a value of positive 544. For 5 seconds, positive 600. And for 6 seconds, 624. And so these are my 3 values that I found very easily using my calculator. Now the other good thing about using your calculator is if you still have your symmetric difference equation in y2, you can use that to approximate your instantaneous velocity at the same locations. So if you have that symmetric difference, then all you need to do is look to the next column in your list, and you will see that the instantaneous velocity, or h prime, of each of these is given right there. So h prime at 4 seconds for me is given to be 72. H prime at 5 seconds is given to be 40. And h prime at 6 seconds is given to be 8. If you did this all by hand rather than using the table in your calculator, this would take you much, much longer. So questions 18 and 19 are related to the data in this table, and that data includes an x-coordinate and a value for the derivative of the function. So keep in mind the derivative is the slope of the function. Now 18 asks us to compare the values at x equals -1 and 2 for the actual function. So keep in mind this is not asking us to just look at the values right here. We have to think for a moment. So the important parts for this are that the slope is always negative. for this interval. So that means from -1, or from x equals -1 to x equals 2, the value for f of x decreases. Therefore, what does that mean for us? That means that f of 2 has to be less than f of -1. That value is decreasing. You could also say f of -1 is greater than f of 2. That is the same thing. But the reason I know that is because this value for the derivative is always negative. Now, these values are changing. So for number 19, we want to know if there's anything we can conclude about the concavity of our function. So let's take a quick second and sketch what this might look like. So if I have a graph, and all I'm doing here is x and f of x, and I want to sketch a graph of this function, all that's going to happen is I have a slope that is negative, and that negative value is getting closer and closer to 0. So I have something that looks like this. So say, imagine my slope is -2.3 here. Oop, actually, let's do it all the way in the negative region. Pardon. So we have a slope that is negative at value -2, and it's less and less negative. So it looks something like this. So my slope is most negative over here at x equals -2, and then it's gradually becoming less negative. So what do we know about the concavity of this? Well, that tells us that this function is concave up, right? If we kept going with this, it would curve back up. Therefore, our function, f of x, is concave up. And that's from looking at the slope, and you can justify this just by giving a graph that approximately looks like the function. Now keep in mind, if you sketch this graph incorrectly, your conclusion would be wrong. So be very careful. For question 20, we are given a big graph of the function f of x, and we are going to sketch a possible graph for its derivative. So in order to do that, I'm going to start by finding some interesting points, or some critical points in my graph. So the first most obvious critical point are the locations where the slope is 0. So this location right here, I would be able to sketch a tangent line and the slope is 0. The same is true at this location. And the same is also true approximately right here. So this is a little tough to read, but we'll go ahead and say that there's just one location where the value of the slope is 0. So I'm going to go ahead and sketch some intervals at the top that will help me sketch my derivative. So to the left of this 0, I see that all of these slopes are positive, right? So the slope of this is positive for this section. So that means that the value, or rather the derivative, I should say, is positive for this section. For the next section, this slope is negative. For this section, the slope is positive. And then the slope is positive again for the remainder over here. So keep in mind, all I'm doing is looking at how does the slope vary from one section to the next. Now, you can go one step further with this, and you can actually say, how does the slope change more specifically? So for example, this slope is very positive, and then it decreases to 0. So I can say this decreases to 0 for this section. Here, I see that I gradually leave 0, become very negative, and then midway through, start to become closer to 0 again. So when I go through and sketch this, right, I keep this in mind the entire time. So I'm going to go through and sketch this. So at 0 is my derivative. So I'm going to graph my derivative as a dark purple here. So this is f prime of x. And so to the left of this, my slope is positive. So my function, or my derivative, is going to be positive and is going to decrease down to 0. So my first section could look like this. Should probably try to line this up a little better. Look like this. Then, my slope is negative, so my function should be my derivative should be negative for the next portion. So it curves down under like this. So this derivative is negative at this point, and then it gets back to 0 at the next point of interest. Then it's positive for the next bit, and let's take a quick look. So it starts at 0, and then it increases, and then it decreases again. So it looks like it does something like this, and it goes back to 0, and then once it gets to 0, it actually increases again. So we could have something that looks like this. So the thought process here is really take a look and work through your function's slope very slowly. And you can do this one section at a time, and you will be just fine. Number 21 asks us to do the opposite of what we just did in number 20. So we're looking at the two functions, v of x and p of x, and we want to know which is the function and which is the derivative. So if I take a quick look at this, I'm going to take a quick look at where each function has a slope of 0. So there's a slope of 0 here, slope of 0 here, and then for the blue function, I have a slope of 0 here, slope of 0 here, the slope of 0 here. So the question then is, can we identify which is the function just based off of when the slopes are 0? And the answer appears to be no, because every time the slope of the blue function is 0, the red function is on the x-axis. So we can't necessarily say that the red function is the derivative of the blue. The same is also true of the red function. The red function, whenever it has a slope of 0, the blue function is also crossing the x-axis. So our 0 values don't really help. So now we need to go to the next part, and let's go ahead and do different colors here. And we'll say at this point, the slope, so we'll say, let's call this v prime of x. Say this is our slope of 0, this is our slope of 0. So let's look at the sign for the slope. So this function is decreasing on the left-hand side, so the slope is negative, and v prime of x would be negative. Then for the middle section, our slope is positive this entire time. And for the final section on the right, this slope is negative. So does that correspond to the values of p of x? So there's a question mark. So is p of x negative for this portion? And the answer is no. So that seems to imply then that v of x is actually equal to the derivative of p of x. So we can say v of x is equal to p prime of x. Now if we want to go ahead and justify that a little further, let's do our points of interest for the blue function down below. And so we'll call this p prime of x. And so here is a 0 slope. Here is a 0 slope. We can see that. And then here is a 0 slope. And the slope to the left is very positive. In this middle section, it is negative. In this section, it is positive. And finally, negative. And so we see then that the value for the red function is in fact positive for this whole section. It all is negative for this section, positive for this section, and negative for this section. So, again, we are justified in saying that the red function, v of x, is the derivative of p of x.